Module 2, Advanced Econometric Methods, Model Evaluation, and Applications. Introduction. Welcome to Module 2 of the course Advanced Statistics and Econometrics I. In Module 1, we explored the core principles of probability theory, estimation, hypothesis testing, and linear regression. Now, we take a step further into advanced econometric techniques, including time series analysis, model specification, simultaneous equations, and model validation. The focus of this module is to equip you with practical tools for handling real-world data complexities. These tools will help you design, estimate, and assess econometric models for economic policy, forecasting, and empirical research. Section 1. Model specification and misspecification. Model specification is the process of choosing the appropriate form and structure of an econometric model. This includes selecting the correct variables, functional form, and assumptions. A correctly specified model should include all relevant variables, exclude irrelevant variables, use the correct mathematical form, satisfy the classical assumptions. Misspecification occurs when any of these conditions are violated. Common forms of model misspecification include omitted variable bias, leaving out important explanatory variables. Inclusion of irrelevant variables, adding variables that do not belong. Incorrect functional form, assuming a linear relationship when the true relationship is nonlinear. Measurement errors, using inaccurate or imprecise data. Misspecified models can yield biased and inconsistent parameter estimates. Econometricians use specification tests such as the Ramsey reset test to detect these problems and refine their models. Section 2. Multicollinearity. Multicollinearity occurs when two or more explanatory variables in a regression model are highly correlated. This causes problems in estimating the individual effect of each variable, leading to inflated standard errors, unstable coefficient estimates, difficulty in assessing variable significance. While multicollinearity does not bias the estimates, it reduces their precision and interpretability. To detect multicollinearity, analysts examine the correlation matrix or use diagnostic tools such as the variance inflation factor or VIF. Solutions include removing or combining correlated variables, or using dimensionality reduction techniques. Section 3. Heteroscedasticity. Heteroscedasticity refers to the situation where the variance of the error term is not constant across observations. This violates the classical regression assumption of homoscedasticity and results in inefficient estimates, invalid standard errors, distorted hypothesis test. Common sources of heteroscedasticity include income disparities, population heterogeneity, or incorrect model specification. Detection methods include graphical analysis and formal tests like the Bruch-Pagan and White test. Remedial measures include using robust standard errors, transforming variables, or adopting weighted least squares estimation. Section 4. Autocorrelation. Autocorrelation, or serial correlation, occurs when the error terms of a model are correlated across time periods. It is especially common in time series data and leads to inefficient parameter estimates, misleading inference results. Positive autocorrelation implies that a positive error tends to be followed by another positive error. Negative autocorrelation means that a positive error is followed by a negative one. To detect autocorrelation, econometricians use the Durbin-Watson statistic or the Bruch-Godfrey test. Remedies include adding lag variables or using generalized least squares methods. Section 5. Time series analysis. Time series data consist of observations collected at regular time intervals. Econometricians use time series models to analyze trends, cycles, seasonality, and make forecasts. Key concepts in time series analysis include stationarity. A stationary time series has constant mean and variance over time. Most models require stationarity for valid results. Autoregressive models. These models express the current value of a variable as a function of its past values. Moving average models. These describe the current value as a function of past errors. ARIMA models, these combine autoregressive and moving average components and allow for differencing to achieve stationarity. Time series analysis plays a central role in macroeconomic forecasting, financial market modeling, and business cycle analysis. Section 6, Unit Root Testing and Cointegration. Non-stationary time series pose challenges for analysis and can lead to spurious regressions. A common method to test for stationarity is the unit root test. Unit root tests, such as the augmented Dickey-Fuller test, are used to check whether a series has a unit root and is therefore non-stationary. Cointegration occurs when two or more non-stationary series move together in a stable, long-term relationship. If variables are cointegrated, it is appropriate to model their relationship using error correction models, which combine short-term dynamics with long-term equilibrium behavior. Section 7, Simultaneous Equation Models. In many economic systems, variables influence each other simultaneously. For example, price and quantity are determined together in supply and demand models. In such cases, single equation models are inadequate. Simultaneous equation models involve multiple equations with endogenous variables appearing on both sides. They require special estimation techniques to avoid simultaneity bias. Common methods include two-stage least squares. 2SLS involves estimating one equation while using instruments for the endogenous variables. Three-stage least squares. 3SLS extends the method to incorporate error correlations across equations. These models are essential for analyzing interdependent economic relationships and policy simulations. Section 8, Instrumental Variables and Endogeneity. Endogeneity arises when an explanatory variable is correlated with the error term, often due to omitted variables, measurement error, or simultaneity. This violates the assumption of exogeneity and leads to biased and inconsistent estimates. The instrumental variable for method is used to resolve endogeneity by replacing the problematic variable with an instrument that is correlated with the endogenous variable, uncorrelated with the error term. For estimation is widely used in labor economics, development studies, and program evaluation. Section 9, Econometric Software and Practical Applications. Modern econometric analysis relies heavily on software tools for estimation, diagnostics, and visualization. Popular software packages include eViews, widely used for time series and forecasting. Stata, popular for cross-sectional and panel data analysis. R and Python, open-source platforms with powerful statistical and machine learning capabilities. SPSS, common in social science research. Econometric software allows users to input data, estimate models, check assumptions, and interpret results. Practical application of these tools is essential for empirical research, academic writing, and policy analysis. Section 10, Policy Evaluation and Forecasting. Econometrics provides powerful tools for evaluating the impact of policies and forecasting future trends. Policy evaluation involves estimating the effects of interventions such as education subsidies, tax reforms, or health programs. Techniques include randomized controlled trials, difference in differences analysis, regression discontinuity design. Forecasting uses time series models to predict economic variables like inflation, unemployment, or GDP growth. Accurate forecasts support informed policy decisions and business planning. Econometric analysis informs stakeholders, supports accountability, and drives evidence-based policymaking. Conclusion of Module 2. This concludes Module 2 of the course Advanced Statistics and Econometrics I. In this module, we covered advanced topics such as model specification, multicollinearity, autocorrelation, heteroscedasticity, time series analysis, cointegration, and simultaneous equations. We also explored instrumental variables, policy evaluation, and the use of econometric software in practical analysis. With this knowledge, you are now equipped to tackle complex econometric problems and apply statistical reasoning to real-world economic data. Together with the foundational concepts from Module 1, you now possess the tools and theoretical grounding to pursue more advanced econometric studies and professional research.